record. So yes, recording is going on. Yes, nice. And it's time to look a little bit at simulation. And this is the topic that really is the labs and project is about simulation. So today there will be a brief introduction really. And I have maybe 1 hour here. We'll see if I how much I will be able to say during my hour here. I think it's okay. So general about simulation and also a little bit about queuing theory, which is a little bit more mathematical stuff. But what's simulation? I think most people have some kind of idea of what is simulation, but I thought it's good to look at an example first. And simulation is really used a lot to simulate the real world inside a computer. And there are many different programs. I found one that is actually free to use and very professional. It's YAMSim, it's called. And let's take a look. But I have a very big screen, so when I start the program, it covers. It's hopelessly big. But I think we can. Let's see. I can make it smaller here. So when I start it, it looks a little bit like this. So this is a general program you can use to model things. You can create models in 3D or 2D, but normally it's mainly more mathematical models. You can have nice physical views of the models if you want, but mainly when you deal with simulations, you don't care so much about the physical view. It's more like how it mathematically works or programmatically works. But this tool, you can actually use build quite nice models, which look visually beautiful as well. But it's a lot of work. I'm no expert in this tool, but we will take a look on some already made examples. When you download the YAMSim, if you want to take a look, it comes with all these examples as well, and that's really, really good. So one example of what you could do with a simulation is this CAFE model. Let's open it. Now it's too big again. Stupid. I need to make it smaller. Let's see. So it looks a little bit like this. So so the model is in the middle here. It's visual, but it's really quite mathematical. So it's when you simulate things using this kind of tool, it's very often different stations, and then you have jobs flowing through these stations. And in this case, you have customers entering a cafe and deciding if they want to do buy a sandwich or sit down at the table. And if they do a sandwich, it's quite easy. They go to the sandwich maker and then they pay at the checkout. If they want a table, it's more complex. Then they also need to seize a waitress, and it takes a longer time. So these are actually kind of mathematical models, and all these things are kind of standard things that you simulate very often in a queuing network. You have jobs and you have queues, you have service stations, And you can model a lot of real world things using these things. Service stations can be computers. The customers can be packets arriving on the internet and whatever. So it fits a lot of real world use cases, these mathematical models. So if we run the simulation, we can see that the jobs enter here, that's the customers. There's a certain probability they want a sandwich or need a table. And if they need a table, they see the waitress and then they eat, and that takes a long time. So here they stay for a very long time. And we see that we have, I think we have how many tables maximum? We can click on the tables and see that we have 100 tables. No, that's not the default value. I have accidentally changed that one, I think. Oops. I think 10 or something is a good capacity. Oh, 10 is maybe too low. 12 is needed now. And there are more customers arriving that are putting queue for the tables now. Oops. So maybe the default something around 16 maybe. No, 20. Now we got the queue for the waitress instead. Oops. But that's okay. Now we have enough tables. Maybe. No, we need 30 tables. Oops. That's good. Now we can reduce the queue here, and we have 30 tables instead. So what can we do using a simulation like this? Well, this simulator is actually quite nice because you can interactively change parameters while the simulation runs. Sometimes, and you can see if it starts to build up queues, these arrows or triangles here are queuing elements. And the customer generator is typically some kind of random generator. It follows a certain random distribution that is determined by this component here. So it's a customer EAT distribution, which means something. I'm not really sure, but maybe it's random from 10 to 50 seconds between each customer arriving or something, I suspect. So this thing here regenerates customers randomly with the spacing in between from 10 to 50 seconds. How long do they stay to eat? Well, that's also determined by eat meal distribution typically here. So let's see. I think maybe it's, I'm not really sure how it mathematically works together, all these things. But you have a customer type, that's a random distribution for having a sandwich or table. And then you have a bit random eating types and things like that. But we can see this is actually real time times 16. So it's 16 times the speed of the real world now. So we could actually quicken up, and then we see how it works when customers arrives here. And we are simulating many hours here now. So, and if we don't want real time, we can actually press this button, and then it simulates as fast as the computer, my computer here, can simulate. And now we are actually simulating months almost here. So this is one of the points of simulation, that you can speed up the things. You can just press a button and simulate 2 years of customers. If in this simulator, the graphics slows down things. Normally, you might only have a mathematical model that simulates 2 years of customers in 1 second, and then you get the result. But if you want this visual nice thing, then you must sacrifice some performance maybe. But it's quite interesting to have this interactive model because, for example, like we saw before, we could have a problem here if we increase the number of customers. Let's say they are very frequent. They arrive from 5 seconds to 20. Now customers are arriving very fast, rush hour, and we see that we are ending up with queues at the sandwich maker and the tables. So now we get into trouble here. All tables are in use, all 30. So we clearly would need to have a faster a sandwich maker or multiple sandwich makers, but we could make it faster. So how long does it take to do a sandwich? We must reduce this to maybe 40 seconds and 10 seconds here. Then maybe we can get rid of the sandwich queue. We need a faster sandwich maker. And tables, okay, let's increase them. We need 300 tables instead. Now it should work. But what happens? Well, we end up with a really, really long queue at the waitress. So maybe we would need 100 waitresses as well. That's better. Oh no, now we get a queue on the payment. Everyone is trying to check out at the same time. Oh no, it's difficult to run a cafe where customers arrive too frequently here. But this is an illustration of what you can do when you simulate. You can try out different scenarios. What if we have more tables? And you can identify bottlenecks and things like that. So this is one idea of what you could do using a simulator. So very often, this is a very complex network, a cafe. Quite often you do much more simple things like a server and queue thing only. And that model look like this only. And you have a generator producing jobs randomly. And you have a server that services the job a little bit random. And a sink. So this is a very easy network, and this is something you could work on yourself in the course maybe, and even do some programming around yourself. It's a very simple server and queue example. What's the interesting things here? Well, if you have the average time between jobs arriving is 1 second, and the service time is less than this, then it will be no problem. The service station here will have no problem keeping up with the jobs arriving. That's some general reasonable thinking. If the service time is longer than the average time between jobs, then we get into trouble and we will have the queue arise here. So if we run this, we can see that it has sometimes a slight queue, but because it's random, the generator, it might be the case sometimes that there are many jobs arriving. But on average, there should be 1 second between each job. But if we change this to 1.2, we get into trouble. Then the service station is too slow. And we will see that the queue should eventually build up more and more. So the longer we simulate, the more time that passes, we get a longer and longer queue. And then we can think about so in real systems, if these were packets arriving to a switch or router or something, we would typically have a limit on the queue. So after a while, it might drop these jobs, and that is also possible. When you simulate, you can create that kind of models and put limited queue lengths and things like that. So a slow server here with faster jobs arriving, that's no good. The system will not be able to keep up, and queues grow. So I think that's enough as an example of some don't save. I turned the YAM sim off here, but it's a quite funny simulator to play around with, actually. And there are actually some simulator games out there, so it can be quite fascinating to build models and simulate stuff. But why do we want to use simulation? Well, it's actually a lot cheaper and faster than to actually build a cafe, maybe, and then start to worry about do we have the correct capacity or something. It can be cheaper and faster to simulate and see how many tables should we have, how many customers can we handle. And sometimes it's safer using simulation. It might be a dangerous system. If we are simulating a plane crash or a car crash, we don't want to do it, really. Then it's better to simulate. And actually, some things you can do in a simulation is kind of impossible, maybe, to try out in the real. If we want 1 million customers per second in a cafe, that's not realistic in the real world, but you can try it in the simulator. So it opens up more strange possibilities, maybe. And you can also do more measurements. So it's easy to kind of inspect queue lengths, waiting times, average things that you want to know. So it's more transparent in some way than the real life. And simulation is used a lot, especially early when you are designing systems, or maybe you want a grasp of the performance. Should we buy 3 or 4 servers? Let's simulate things and see what kind of numbers we end up with here. So it's a useful tool early in a design of systems, or planning when you're planning to build things. Simulation can also be good when you're actually trying to find problems in systems. Then if you model an existing system, you might be able to use simulation to actually find out what happens and why things happen. So it's very often used for, yeah. But when you simulate, you need a model. And models are actually useful besides simulation as well. When you develop systems as a software developer, you very often use models to actually kind of test out things, sometimes using simulation, sometimes using formal mathematical tools, and sometimes using kind of software testing approaches. Sometimes you use models to actually generate your programs or code. And there is a whole field called model-driven development. And this is quite interesting, actually, because then you create a model and you can generate your code and programs from that model. And at the same time, you can test and simulate things using the same model. And that means the the thing you simulate and test will be exactly the same as the thing in the real world later on. So that's very powerful. And this is even more fancy today, maybe. If you read in papers, you can read about digital twins. It's a buzzword today. That means a model that you really use for simulation maybe, or testing or something. But a digital twin, then you keep the model updated as well. So when you have the real system, for example, in the cafe, you do measurements in the cafe and feedback those data to the model. That means you have a model that is always kind of up to date with how the real world looks like. And then you can start using this more accurate model for different things like planning or change studies. What if we redo our cafe in some way? We have a very accurate model because we keep this kind of digital twin. The cafe exists as a model in the computer as well and should be identical in some way. So models are useful not only for simulation, but they are very useful for simulation as well. So there are different types of simulators and simulations. We have some, and the most common ones in the computer area, when you simulate computer stuff, is really these different. The more general one is the discrete event simulation. That's what we saw in YAML-Sim. You have a lot of events occurring, that jobs arriving and things like that. That kind of simulator is very general and very popular for network technology. And so there are some network simulators. You have, for example, some Cisco specific, like Packet Tracer and things. But there are also some more research tools. And the most popular today is maybe NS3 and Omnet. We are going to use Omnet in the course later on. I think that's one of the more easier things to use, but still very, very complex actually. NS3 is more complex. You need to be more skilled with programming, and it's both environments use C++ actually for creating models, but Omnet is more graphical, and you can do without some programming if you're lucky. But the discrete event simulation is the most general and kind of common way of doing it. But there are actually other ways of doing stuff. You can use, well, the network simulators very often rely on random packets, random jobs, random things. But you could also use traced event simulation. Then you, instead of random things, you record the real world and maybe drive the simulation using a kind of log from the real world, or trace from the real world. So, and that can typically be combined. So if you have real traffic, network traffic you have recorded, you can use that as a kind of trace for driving a simulator model that you have created. And in the extreme case, this becomes a kind of program execution simulator. That is, you have a simulator that simulates a computer by running a program on it as well. So these kind of tools are very powerful. One example of them is Simix, and we can take a look on that page maybe. Let's see. It's a fairly expensive simulator, but this simulator has modules and things that you can actually simulate computer systems, not only single computers, but many computers and networks between them. And it simulates them in such detail, so you can actually, inside the simulator, you can use normal software like operating systems, applications, whatever. It's very, very slow compared to the real world, but it can, I'm not sure, you can boot up Linux and Windows and things like that inside the simulator. Why would you want to do this? Well, this tool, Symix, is actually used by for example, by Intel and the big manufacturers of computers. If you have this simulator, you can run application operating systems, and then you can start tweaking models. What if we do this slight change in the processor here? And they can actually experiment with changes inside the processor and see if it gets better performance from different applications and things. So it's quite powerful actually, and slightly expensive, I think, if you want to actually use it for commercial things. So yeah, but this is a kind of tricky. Yeah, so it's a program execution simulator. So it's a kind of special thing. You really run unaltered programs on it. That's not typically what we will do. We will build kind of event models instead and do simpler stuff. Probably, we'll see. Yes, so for example, Symix works by actually interpreting each program machine instruction, and that drives the simulation of the whole machine model in some way. In the simulators we are, and in YAMSim and Omnet we will be working with, it's a discrete event simulation. And there you typically generate jobs like events, and you have a queue that holds all the events in the system. These simulators are quite easy to build actually. The simulator core is a very few lines of code if you would like to build it yourself. But to make it more convenient to work with, it might be slightly more complex. But if you want to build this kind of simulator, you need kind of events to handle, and you need a queue to hold them, and you just sort them with a future time. When should this event happen? And the simulator works by picking the next event to process in time from the queue, and then executing or handling that event, which typically generates new events. So you model all your things. The simulation model is a model that generates or translates events. There have been some special languages invented sometimes for these things, but it's perfectly all right to do general purpose stuff as well, with normal languages, programming languages. This is an example of inside such a simulator, like YAMSim. Somewhere deep inside the simulation core, it looks like this, typically in all these simulators. So you have a loop forever, where you have an event queue. You pick the next event, depending on the current simulated time. That's not the real time, it's the virtual time, which can jump very quickly. So you get the next event, you check, is it time to stop the simulation at some point in the future, maybe? Just simulate 1 year or maybe, or something of simulation. Then you should stop. Otherwise, you take a look on what kind of event is this? Is it a job arrival? Is it some service station that is ready? Or some other event or something? And then you act by creating typically new events, new jobs, and put it in the same event queue in the future sometimes. So you get the current time plus some random time in the future, and you generate a new job. And that's typically the thing you do. The model, this is the model, but writing it in this way, it's really clumsy. If you have 100 service stations, you get 100 case statements here. It's very clumsy, and you want a more object-oriented or graphical way of putting it all together. And that you get from different frameworks and tools. So, yep.
Fråga en sak bara, är det här case som står där under switch eller så här? Är det typ som if, alltså typ om det är eventjobb så startar den där eller så startar den där? Eller ja.
Yes, switch in this case is like a if statement. So switch, depending on what event you picked, the events are of different kinds here. So if it's a job arrival, it does these things. If it's a service station ready, it does these things. So it's like multiple if statements. It's the same thing. And what is the actual simulation code here? It's the core of the simulator is only these few lines. The rest is the model that you want. What behavior are you thinking about when the job arrives? You should do something here. But you don't really want to work like this. Later in the course, we will take a look at the Python framework, where you actually have a more process-oriented or object-oriented way of describing what happens when an event arrives, when jobs arrive. This way of writing a simulator would work, but when the model grows, it becomes quite clumsy here. So, but it can illustrate how actually simple a simulation, when you program it yourself, it's not very difficult actually. The problem is when it gets bigger to get nicer and manageable. So there are a lot of tools, and we will look at the Omnet tools and also the SymPy framework in Python during the labs. If you don't know Python, you will concentrate on Omnet. If you know Python, you can maybe try out both. There is 4 different tasks where you can choose 2. 2 Omnet exercises and 2 SymPy exercises. So you can actually choose if you want to concentrate on one of these or both or whatever. It's mainly the thinking is that you should pick one of these maybe for the project later. But actually for the project, you can pick whatever. There are a lot of tools available. These are some network simulation tools like NS2, NS3, OpNet, NetSim. These are networking simulators. Then we have the YAMSim or some other more general discrete event simulations where you can build whatever you want. And YAMSim is actually quite nice as from a graphical. It's very graphical and nice. So can you use Cisco Packet Tracer? Well, it's also a simulator. But one problem with some of these basic simulators is that they don't allow any timing model. If you try to do network simulation with the packet tracer here, you won't get any timeout, real time. When a packet is sent on a link in packet tracer, it typically takes 0 time or a unit time only, regardless of the length of the link. So if you want to do performance studies and measurements, the Cisco packet tracer is useless. You have no timing information. So all these other simulators have actually a lot of already written timing models for a lot of stuff. So in Omnet, for example, most things on the internet is modeled, and you can actually get detailed performance numbers out of it. So yes, Cisco Packet Tracer, very useful if you want to experiment and learn things. But when you want to do measurements and studies, you want something else. And the SymPy, we will take a look on it later on. You can find that similar kind of frameworks in all languages. So depending on what your favorite language, if it's Java or C# or whatever, you can find a simulation framework or library to help you actually. It's very, very common. So if you like Java, you can do Java Sim, or Python is SymPy, and yeah, JavaScript, you have a SimJS helper. So people in all languages likes to do simulation, and there are a lot of frameworks and libraries available. And they are actually a little bit similar. So, yeah, there are some ideas that you find everywhere. So, okay, well, a little bit about simulators. We saw that the YAMSIM, for example, when you model things, it's typically the basic thing at the bottom is actually a queuing network and queuing simulations. All these discrete event simulators work with these kind of components. And if you have a very simple network, it's actually possible to compute things without simulation. You can do it mathematically. And that area of maths, or it's called queuing statistics or queuing theory. You can buy books about queuing theory. And that's, if you like maths and don't like simulation, you can actually try to calculate stuff using formulas instead of simulating stuff. But it only works for very small networks, I would say. So, but from a modeling point of view, it's good to have seen it. So basic model is actually consists of a lot of service stations, and you have queues in front of the service stations, and you have customers arriving. So you have something generating jobs. So that's the building blocks. And very often you can, well, you can illustrate it with these pictures, maybe jobs arriving. You have a queue and you have a service station. If the service station is really fast, you will seldom end up with a large queue. But if the jobs arrive quite randomly, might be the case that many jobs arrive in a very short time, then you actually need the queue to handle the burst. Because the server might be kind of quite fast, but more regular and not super fast. So, but this is a way of modeling things as jobs, queues, and resources. And those concepts you find in most frameworks, like in the SymPy. When you program, you have typically resources, queues, and jobs that you work with. So jobs arriving, it's very common to model them in some standard ways. So one way of doing it is to have periodic events. You have something to generate jobs, which is exactly the same inter-arrival time, like equals 0.1 second. Or you can have sporadic. That means it's at least 0.1 seconds. It cannot be faster, but it can be slower. So it can be more seldom here. Periodic is quite useful and very, very often used. Sporadic, not so much, but the most common modeling thing is the stochastic. It's almost default in many components and frameworks. So what does that mean? Well, then you have a random inter-arrival time. So it's the time between two jobs here are random. And it can be random all down to almost very small, like almost 0 seconds between two jobs. And that means you can get like bursts with more frequent jobs sometimes. Yes, so yeah, if you have this periodic arrival, it's very, very easy. If you have a service station handling periodic arrivals, then if you know that there are 0.1 second between each job, if you can handle 10 jobs per second or more in the service station, it's okay. Then the system is kind of stable. Jobs are not arriving too fast for the service station. So that's very easy. And if the service station is slower, you will have a queue buildup. So it's very easy to know what will happen if you have this constant inter-arrival rate. If you have a random arrival rate, it's more tricky. And one of the most popular modeling network or basic network that you can also calculate mathematically and simulate quite easily is the MM1 queuing network. M stands for memoryless, and it's the same as the Poisson distributed arrival inter-arrival times, and that's just a statistical distribution. It's the exponential distribution. So this is very common, and what does it stand for? Well, M stands for the job arrival, and the next memoryless is the service station time, which is also random, and then one that you have one service station. So this is a random inter-arrival time with a random service time and one station. That's the MM1 network, and it's simple enough that you can actually calculate everything theoretically, but it's also quite simple to simulate and very popular to simulate. What does it mean with the Poisson arrival? Well, then for each job, you randomly pick an X here, an inter-arrival time. And this is the probability here. So lower spaces between jobs are more common. But if you're in a rare case, you can get a very long inter-arrival time. So large gaps happens, but they are rare. Smaller gaps are much more common. But this distribution in statistics actually has an average value, a mean, and that you can calculate by this lambda parameter here. So lambda is the arrival rate. It's 1 divided by the inter-arrival time, which is, it could be 50 jobs per minute. Then the inter-arrival time is 0.02 minutes. So the average is 1 divided by this. So you can have really small inter-arrival times, you can have large, but on average, it follows this 1 divided by lambda parameter. That means that you get some kind of predictability anyway, because if the server can handle more jobs per minute than what's arriving on average, then the system is stable. Sure, the randomness means there can be really large bursts sometimes. So it puts more emphasis on queues and things. But on average, the system will be stable. So that's the nice thing about this. But the randomness is a little bit funny, actually. We can take a look. Oh, yes, we will take a look on a simple model here. But first, this one. This is how it really a system might behave. So if you have the load, that means the processing time of the service station divided by the arrival time on average here. So if you have 100% load, incoming jobs fully saturates the server here in some way, it will not be good. The waiting time for each job latency increases up to infinity. But if you have a low load, that is, the service station is much faster than what jobs are arriving, you still get a slight queue. You don't get zero waiting time because of the randomness. So, but it's no problem until you reach maybe 80–90% of the capacity. This is a good diagram to carry with you. It explains a lot of how systems work when they get overloaded. So, and the randomness tells you that the overload starts to happen really not at 100%, but maybe 80 or 90% here. If you had perfectly predictable regular arrival times, you would get zero waiting time up until 100% when it goes to infinity and you start to get queues in some way. But the randomness makes this a little bit more, the queue gets more important, actually. But let's end this by looking at this example. Someone has hosted this simulator JavaScript framework on a website somewhere. The link disappears and appears every year at some new place because it's an open source framework, but no one wants to host it. But I found it here this year. Let's see. So when you run the JavaScript, it looks like this. So it's like a very simple graphical discrete events simulator. And I have some examples. For example, I have the MM1 queuing network. It's really nice if you want to play around a bit. So you have a source that produces jobs using this memoryless distribution, that is the exponential distribution or Poisson process. Its inter-arrival rate is set at 0.25, and we can pretend it's hours maybe, or seconds or something. If we click and double click, we can actually change our lambda here, the arrival rate parameters. So we have 0.25 jobs per second on average, because now we are using this random process. We have a queue. We can check the queue. It's infinite in length. And the service rate for the station here is 1 customer per second. And we can see directly that this network should have no problem. We get a new job produced each 4th second or something, but this can handle 1 each second. So yes, so if we simulate this, it's not as visual as before. It simulates 4,000 hours directly, very quickly. Now it has finished simulating 4,000 hours, and we get the results here. And we can see that there were 3,600 jobs arriving to the service station queue. The server was utilized approximately 1/4 of the time, 24–25%. Time spent in the queue on average is only 0.29 seconds. And time spent in the whole system, it takes 1 second to be processed. So it's 1 second more approximately here. The length of the queue was very small. sometimes we had a job in the queue, but it was mainly empty. It's 0.074. So we get some nice statistics here. And of course, now we can start playing around if we want. We can, for example, say that we have 1 or 0.9 arrivals per second. That means that we are closing in on the 100% load here. So now we should see slightly more queue lengths. It's still stable because this is less than what the service station can handle. So if we simulate this, we can see that we have almost 90% utilization now. We have a lot of several more arrivals. We have quite long queue now. We have six on average in queue, and it's still stable. It's not overloaded, but because of the randomness, we get a slight queue here. And what happens if we go above the capacity of the station here? Well, queues grow. But depending on how long we run this simulation now, because the longer we run the simulation for, it's the longer the queue will get. So now we have 600 jobs in the queue here waiting. But if we double the number of hours here, we should get probably double the length here. It grows linearly. But it's quite fun. You can experiment with the different things. 0.8 arrival, and then we put that our queue can only handle 10 jobs. What happens? Well, we get different numbers. We get server utilization 77%, and we have 200 dropped jobs now. The queue accidentally became full sometimes, and the jobs were dropped. So, well, it's a very simple model with random times here and random times here and a queue. So, and we can get some statistics from it. So there are a lot of more complex models you can build. This JavaScript framework is actually maybe a bit simpler if you have a smaller model than this more fancy YAM sim tool. But it shows the principles in some way of how these networks can be modeled and simulated. Okay, so it was really the last example here of the simulation things. Okay, thank you. And I will do numbers, talk about numbers in some future slot in the course. We'll see. I didn't have the time for everything today.